Geometry, section 1-1. Got 3 definitions for you here and 3 examples. I would highly recommend that you take notes. And in my opinion, when you write things, you tend to learn them better. And if this were a traditional year and you were in my classroom during notes, what I would have you do is write them down. I would be writing this on my whiteboard and showing you examples on my screen. Obviously, at the end of the day, that's up to you, but my recommendation is that you write these down. Have a place in your notebook where that's going to be dedicated to your notes, and then have a different place in your notebook that's going to be dedicated to bookwork. And that's what I think you should do. I think that's what gives you the best chance. So in geometry, we start with a lot of language. And geometry, much more than any other math course you'll take, deals with language. So obviously, in the first part of the book, we got to get a lot of the words out there, a lot of the words that we're going to use in geometry, and that's exactly what happens in especially chapters 1 and 2. So here's the one we start with. It's called inductive reasoning, and the definition of that is simply reasoning based on patterns you observe. And I'll show you an example of that. So for this first example, you've got 384, 192, and then 96, and then 48. And the directions are telling us to find the pattern and use the pattern to show the next 2 terms in the sequence. Now, I'll tell you, there are some problems in the homework that have these same directions. And if you want to describe, find the pattern and describe it that way, that's fine. I mean, I bet you could just describe this one here in short order. We're really interested in the next 2 terms, though, right? And I say that because some of them, it's kind of hard to describe what's happening actually. But you will still have not too much problem coming up with the next 2 terms. So obviously here, it's being cut in half. And you could confirm that with a calculator if you want to. But 384 cut in half would be 192. 192 cut in half would be 96. 96 in half is 48. So then if you took 48 and you cut that in half, you would expect the next number then to be 24. And if you cut that in half, the next number would be 12. This type of reasoning that you used to come up with 24 and 12 is inductive reasoning. You recognized a pattern, okay? Now, a lot of times when I teach this example in class, someone will say divide by 2 or divide in half. I'm not even sure what words I just used a minute ago. Really what you are is multiplying by half or dividing by 2. That's the same thing. I tend toward more of an algebra approach, which would say times 1/2. Okay? And if you take that approach on the homework, that might help you a little bit. That's just a tip. All right. Second word that we have today is conjecture. And a conjecture is a conclusion reached using inductive reasoning. So we made a conclusion in that last example with the next 2 terms. Those were conjectures. I mean, does it have to be that? Well, I can't think of what else it could possibly be, 24 and 12. But it really is a conjecture, not 100% for sure. And it's a conclusion reached using inductive reasoning, the type of reasoning that we identified as the first definition. So let's again take a look at an example. That first one here, this was pretty easy. This one might stretch your brain just a little bit more. It says, make a conjecture about the sum of the cubes of the first 25 counting numbers. Okay, now let me make sure you understand what they're asking. Cube means to the 3rd power, right? So, and counting numbers would be like the whole numbers, except they don't start at 0, they start at 1. So 1, 2, 3, 4, 5, all the way to 25, those are the counting numbers. And if we took the sum, meaning add them up, of the cubes, meaning to the 3rd power, of the first 25 numbers, we want to make a conjecture. Okay, now they help us out with this by using this table. And what I would ask you to do right now is actually pause the video and make sure you understand what this table is saying. And I'll give you a little bit of a lead here. So here's 1 cubed, and obviously 1 to the 3rd power is 1 times 1 times 1, so that's 1. And then they're making the observation. They're kind of inferring this for us, that that's actually 1 squared, and not a shock that that's actually 1 squared. But they're going somewhere with this. This is just the first line. Okay, the first 2 counting numbers, 1 cubed plus 2 cubed. The cubes of the first 2 counting numbers. Well, do the math on that. It comes out to 9, and 9 happens to be 3 squared. And that happens to be 1 plus 2 squared. Okay, now again, if you would, pause the video and make sure you understand what the rest of this table is saying, and try to maybe infer then, use inductive reasoning, what the 25th line would be. And then when you've done that, come back to the video. And welcome back to the video. I didn't pause it, but you were supposed to. And again, now hopefully you kind of directed your attention to this column right here, and you made a conjecture that, and I like to use ... when lists get long. So basically the conjecture is this, that 1 cubed plus 2 cubed plus 3 cubed plus ... all the way to 25 cubed would be equal to some number here, I don't know what it is, would be equal to that number's square root, squared, if you will. I don't know what that number is either. I'm sure it's large. Okay, but here's what we're looking for. We would conclude that this is 1 plus 2 plus 3 in parentheses plus ... all the way to 25 squared. Now, you say, why is that any better? You might ask that question. I mean, why is this any better than this? Or why is, what we concluded down here in the bottom right any better than this? Well, think about it if you had to type it into your calculator. You have a to the button, right, to do third power. Usually, most calculators have that. So that would be 1 to the third. That's 3 buttons. Plus 2 to the third. Plus 3 to the third. Versus opening a parenthesis and just going 1 plus 2 plus 3 plus 4 plus 5 all the way to 25. And then close the parentheses and square it, or on other calculators, or another method that you could use on any calculator really would be to push enter and then square that number. You wouldn't even need the parentheses then. Okay, the keystrokes here would be much shorter. All right, now again, that's using inductive reasoning, and we did make a conjecture there, and our conjecture is really that this equals this. And to find out what these numbers would be, this and this, we would have to type that into our calculator, and that's what it would be. And the sum of them without the squared, that would be what this number is to the second power. I don't know if that made sense exactly, but my heart was in the right place, I promise. One more thing about this example. There is a pattern in these numbers right here. See if you can figure out what it is. Again, if you'd like to pause the video just a second, see if you can figure out what the pattern is in this column right here. And what it ends up being is that the difference between them is enlarging by 1. The difference between 3 and 1 is 2. The difference between 6 and 3 is 3. The difference between 10 and 6 is 4. The difference between 15 and 10 is 5. And that pattern would, of course, continue. All right, let's wrap this lesson up with one more definition and one more example. The last word is counterexample, and the definition of that is it is a specific example for a conjecture that is incorrect. You're going to come up with something, some kind of an example that basically proves the conjecture false. And there with the star, it says one counterexample disproves a conjecture. One counterexample disproves a conjecture. If something is true some of the time but not all of the time, and you can come up with one counterexample, the statement is considered false. If it's true some of the time, it's not true. As I sit here and make this video in my classroom on Sunday, August 30th, the day before school starts, I look out my window and the sun is shining. And if I just concluded that the sun shines every day, it wouldn't take too long. I would just have to wait a few days probably and wait for the first cloudy day, and I have my counterexample. That's what that one day proves all the other sunny days, proves the conjecture false, even though we had a whole bunch of other sunny days. All right. And the last example then says to find a counterexample for each conjecture. How about this? A number is always greater than its reciprocal. Reciprocal, you might think of like flip the fraction, right? So the reciprocal of 5 over 2 is 2 over 5, that kind of thing. So think of a number that is always, what you're really supposed to do is think of a number that would prove this false, a number that isn't always greater than its reciprocal, okay? How about 1/2? 1/2 has a reciprocal of 2, and 1/2 is not greater than 2. 1/2 is a counterexample because it proves this statement false. And really any fraction that's top over bottom, small number over larger number would actually work here. How about 1/5? How about 2/7? 9/10? All of these would be the case. There's one other one that I want to point out, and that would be 1. 1 is like saying 1 over 1. Its reciprocal would also be 1 over 1. So the reciprocal of 1 is really just 1, and 1 is not greater than itself. So that is also a counterexample. How about the last one there? If a number is divisible by 5, then it is divisible by 10. Meaning that when you divide, there's no remainder, right? Divisible means, that's what divisible means. So a number that's divisible by 5, then it's also divisible by 10. Can you come up with a counterexample to that? How about 15? 15 is divisible by 5. It's not divisible by 10. Really, wouldn't it be the case that any number that ends in 5 would be a counterexample here? 25, 35, 185. Those are all divisible by 5, not divisible by 10. Okay, now that's the lesson. I got one more thing I want to tell you about number 7 on your homework. And if you like a challenge, then again, before I give this away, maybe you stop the video and try to challenge yourself on that one. But I'm going to give away an answer right now otherwise, okay? So this is number 7 on your homework, and students just had trouble with this in the past. So I'll just give it to you if you want to know. Otherwise, you've stopped the video. I don't want to blow it for you for somebody who wants to challenge themselves. You're doing the inductive reasoning. You're trying to figure out a pattern. Think of the letters that the words of numbers start with. So, for example, 1 is spelled O-N-E. Okay. Now, I'm not giving it completely away, but that in effect probably does give it away. So that's number 7, and that was your hint. All right. Well, thank you for tuning in.